The next significant wind we will look at is the gradient wind. This wind is identical in almost every manner to the geostrophic, except that it blows along curved isobars as opposed to straight isobars. You will remember that this curved flow created an additional force, namely the centrifugal force. So for a gradient wind, we can say that there are principally three forces: pressure gradient force, Coriolis force, and centrifugal force. So how will the additional force interact with this wind? Looking at a high pressure in the northern hemisphere, we can see a Coriolis force and the pressure gradient force acting on the wind. If we now place this picture on the circular isobar around the high, we will need to add the additional centrifugal force. Notice the outward acting centrifugal force is helping the pressure gradient force. This will increase the wind speed. Therefore, as a result of the additional force, the gradient wind around a high is faster than the geostrophic, even though the isobar spacing of the two winds is the same. The gradient wind is a truer indication of what the wind is actually doing. So around a centre of a high pressure, just remember that the gradient wind is slightly faster than the geostrophic wind. Let's look at the gradient wind around a low pressure system. If we add the centrifugal force, notice that this time it opposes the pressure gradient force. This will reduce the wind speed. Therefore, as a result of the additional force, the gradient wind around a low is slower than the geostrophic, even though the isobar spacing of the two winds is the same. So, around a low pressure, just remember that the gradient wind is slightly slower than the geostrophic wind. Comparing the two systems, we can see that they both have exactly the same spaced isobars. But because of the additional forces, the wind around the low system will be a little slower than around a high. In the real atmosphere, though, it is seldom the case that the two systems will have identically spaced isobars. As we know, low pressures do tend to have more closely spaced isobars than high pressures, and therefore they have stronger winds. But if they had identically spaced isobars at the same latitude, then the high pressure would have a higher gradient wind speed. The winds we have discussed so far are fundamental and require a considerable time to understand. The rest of this lesson deals with more localized winds which are easier to understand and remember. The first of these are land and sea breezes. Land and sea breezes are local winds that can be found along coastlines, particularly in the tropics. They can only be observed when the general wind conditions are slack, and there are no major pressure systems dominating the coastal regions. The diagram shows a cross-section of the land and sea along a coast during the day. The land will heat up faster than the sea, and will therefore be warmer. As a result, there will be warmer, less dense air above the land surface than above the surface of the sea. This will cause a localized reduction in pressure, and air will start to be drawn in from over the sea. This air will be heated and start to rise. This airflow from the sea to the land is known as a sea breeze, and its strength will be maximum at about 1500 hours. In fact, this localized flow of air creates a circulation pattern up to approximately 1,000 feet, as shown. A good indication of land to a pilot lost at sea during the day is to look for cloud developments over the coastline as shown. Let's look at what will happen at night. The diagram shows a cross-section of the land and sea along a coast during the night. The land will cool down faster than the sea and will therefore be much cooler. As a result, there will be warmer, less dense air above the sea surface than above the land. This will cause a localized reduction in pressure, and air will start to be drawn in from over the land towards the sea. This air will be heated and start to rise. This airflow from the land to the sea is known as a land breeze, and its strength will be maximum just after sunrise, where we have the minimum land surface temperatures. Again, this flow of air creates a circulation pattern up to approximately 1,000 feet. The land and sea breezes are relatively small scale and change diurnally. However, this effect of the land and sea temperature variation can be seen over continental coastlines between winter and summer. These winds are collectively known as monsoons. Shown here is a landmass in winter. As a result of the cooling that will take place, a cold anticyclone will develop and air will move from the land towards the sea. This type of monsoon is relatively cool and dry, since the air has come from a cold continent. Little weather will be observed with this type of monsoon. However, in summer, the landmass will heat up and a low pressure will develop, drawing very moist air from the sea to the land. This air will be forced to rise and cool adiabatically. This will create huge cloud development with large intense thunderstorm activity across the entire coastline region. This type of monsoon is very significant and needs to be monitored carefully for potential hazards to aircraft. These monsoons will be discussed in more detail in the area climatology lesson. There are two other types of localized winds. Again, these can only be observed when the general wind conditions are slack, and there are no major pressure systems dominating the region. They are called anabatic and katabatic winds. Looking at the diagram, we have a sloping terrain either side of a valley. During the day, the land will warm, and in turn warm the air adjacent to the surface. This air will be less dense and start to flow up the valley sides. These valley winds are called anabatic winds. Sometimes clouds on the top of the ridges are signs that these winds are present. Always treat mountain ridges with extra caution, regardless of the clouds that may or may not be present. During the night we can see the reverse effect. The slope surface will cool faster than the air in the valley, and the overlying air will become heavier and denser. As a result, it will sink down the sloping terrain and collect in the valley bottom below. This wind is called a katabatic wind. Throughout the night, cold air will continue to collect in the valley, and the dew point may eventually be reached. This can lead to the formation of valley fog. Good examples of katabatically induced winds are the Mistral, which blows into the Mediterranean, and the Bora, which blows down the Carpathian mountain range into the Adriatic Sea. The last wind that needs discussion is the Föhn wind. This wind is caused when stable air flows over a mountain and descends down the other side. As air is forced over a mountain, it will cool at the dry adiabatic lapse rate of 3 degrees per 1,000 feet until it forms cloud. From then on, if forced ascent continues, it cools at the SALR. There may be precipitation produced on the windward slope, which reduces the water content of the air mass. However, because the air is stable, it will flow back down the leeward side of the mountain, and because it is descending, it will warm adiabatically. At first it warms at the SALR until the cloud disperses, and then at the DALR as it descends further. Because there has been a loss of water vapour from the air, the base is higher on the leeward side than the windward side. Therefore, the descending air will begin warming at the DALR at a higher level. This means that when the air reaches the valley floor again, it has gone through a warming process due to the loss of precipitation over the mountain. A good example is found on the southern slopes of the Alps, as air flows into the Mediterranean during the winter months. We find these winds elsewhere, for example in the Rockies. There they are called the Chinooks. This completes the lesson on low-level winds. Ensure you know the difference between the geostrophic and gradient wind, especially how the forces interact and change. Surface winds are always best understood when comparing them to the geostrophic, so be sure to remember how the two types of wind differ in direction and speed. Whenever you examine a pressure chart to find the winds to help in flight planning, do not forget to also bear in mind the local effects of hills, valleys and sloping terrain. These may significantly alter the wind from what is suggested by the surface pressure chart.